Right, so we start with this LC circuit, circuit only containing an inductor and a capacitor, and we'll go ahead and start with it at this point where all of the energy of this circuit is stored in this electric field. And we're missing the second set where it shows that there's nothing in the magnetic field. From this point, the mass of electrons here would start pushing electrons away, and that would mean a current which is going the opposite direction. This would be high, that would be low. It would push a current around this way, which gives rise to a magnetic field. Now, it's a little bit hard to see, but this loop comes around and that goes in front and then it goes to the back. So if you had current flowing through this loop, as I am tracing it here, can you confirm that the magnetic field would be as indicated? You notice it's not an infinite inductor, or we'd have zero magnetic field out here, but they have the magnetic field going up through the middle and down around the outside. Is that correct for the current going like this? I was just testing it out. Notice the electric field is getting weaker as the magnetic field goes stronger. Boom, boom. And then finally, this thing will completely discharge, at which point you will have maximum current, that when this is not electrically getting in the way of current moving, then the current moves very freely. It's very easy to deposit more charge onto this thing when it is uncharged, and so you have maximum current. But all of the energy is now in the magnetic field. Now notice, this magnetic field then begins to decay because the current will begin to decay. Current still flowing in the same direction here, but as the current is decreasing, still flowing around like that, is that going to produce this? Okay, yeah, this magnetic field is decreasing, still in the same direction. Wasn't expecting that. Okay, and the this current begins to build up positive charge here and negative charge there. So the electric field begins to rise, but in the opposite direction to what it was before. And then finally you have this point where all the energy has gone from the magnetic field and all of it is sitting in the electric field again. And then the cycle begins again, but everything in the opposite direction. The currents flowing in the opposite direction, the magnetic fields in the opposite direction. And so you have this oscillation of the energy between being in the magnetic field and being in the electric field. That I hope you remember an event back in, I think it was one of the early chapters in the fall, where we had the energy going between gravitational potential and kinetic for a pendulum. As it went through the equilibrium position, it was all kinetic, and when it got to an extreme, it was all gravitational potential, but the energy oscillating back and forth between the two. Well, the same sort of oscillation of energy going on here, for what it's worth. Now the real heart of this lesson, and that is for a system being driven. I have an alternating current here that sometimes pushes the current in one direction and sometimes pushes the current in the other, and the frequency with which this alternates is going to be the frequency of the driving of this system. And then I do have an LCR in this circuit, and it's going to cause rather interesting behavior that is going to be exactly analogous to the experience we had before with a spring and a mass and a paddle in the water, a damping part of the circuit. That here too we were driving this, and the driving frequency could or could not match the natural frequency. Well, this one is going to have a natural frequency, and when you drive it at the natural frequency, I would expect maximum amplitude, meaning maximum current flowing in this circuit, minimum resistance to current flowing. The same way here, when you push it drive it at its natural frequency, the driving frequency we called omega d, and the natural frequency is omega naught, then this goes into resonance and you get maximum amplitude response. That please note each of these parts, that here you have energy of position in the spring and the capacitor. It has to do with geometry. Here, how you've arranged charge, and here how much the spring has been stretched or not. In both cases, there is a sort of a restoring force here, that this has a bouncy quality about it. As you push charge on, an electric field is created that tries to push the charge back the other way, in the same way that when you stretch this, a responding force occurs that tries to pull it back. Here what you have is energy of movement, or resistance to change in the motion, sort of the inertial quality of the thing, that here the inductor doesn't like change, it resists change, and if the change is that you're trying to build up more current here, it pushes back. But if the change is that the current is going away, it also pushes to say, no, keep going, I don't like change, keep doing what you're doing. So this one tending to keep the current doing the same thing. If it's going away, it says keep on going. If it's coming on, it says no, don't come on. In the same way that this mass says we like to keep doing what we're doing. And finally, this would be the place where energy is dissipated. Here you have a resistor which turns electrical energy into heat, and here this paddle stirring up this fluid would turn the mechanical energy into heat. So a very nice comparison between these two, which we will milk. Recall that for this spring mass system, the natural frequency had to do with the elastic constant divided by the mass. Well, look at this equation for energy of position, the energy in a capacitor, and this equation for energy of position, the energy in a spring. And they're rather similar. They're both divided by 1/2. They both have this position issue. Here it's charge, but where the charge is mattering. The charge squared, x squared. They compare this, and we see that 1/c seems to correspond to the spring constant. If you go down here, here's the energy in an inductor. Here's the kinetic energy. And again, we're dividing by 1/2. And here it is charge moving, so it's I squared, and here it is just motion, v squared, the mass moving. And so L and M seem to have a nice correspondence. Well then, if we take that idea and come here, then I ought to replace K by 1/c and M by L, and we get this expression for the natural frequency of an LCR circuit. Well, I'm going to show you that that is indeed the case. And for both of these two, as the driving frequency approaches the natural frequency, you do get this condition of maximum amplitude, that we speak of as resonance. Well, this was by analogy I got this result. Let's prove it. Proof? Question mark? Here I'm dealing with the LCR circuit, here the spring mass circuit. And the energy in this circuit is going to be made up of the energy in the capacitor and the energy in the inductor. And here the energy is made up of the energy in the spring and the energy of motion, the energy in the mass, if you like. And then I'm going to take the derivative of these two with respect to time. Notice energy is conserved, so the change in energy with time is going to be 0. So this term goes to 0, and if you take the derivative of this, you get this, and if you take the derivative of that, you get this. Similarly here, take the derivative. Then I'm going to replace I here by dq dt, and I'll replace v here by dx dt. And so we have this second degree differential equation. This is the I dt would be the second derivative of, di dt. I is the derivative of q with respect to time, and so di dt would be the second derivative of q with respect to time squared. And this dq dt in these two I can just divide out because it's in both terms. And so you have q over c is equal to L and the second derivative of q with respect to time. In the same way here, and we derived this last fall, that the dx dt I can algebraically make disappear, and dv dt is the derivative of velocity with respect to time. It's the second derivative of position with respect to time. Boom, second degree. And then we found that a solution to this equation was that the maximum displacement times the cosine of omega t plus phi. And that same solution would work here. If you don't believe it, take the second derivative of this, which is this, take the second derivative of that, which is this, and plug them back into the equation, and you'll find that it does make a good solution to the equation. So we have putting those things, there I am, putting them in. And it makes a good solution when I replace q by this thing, and I left out all the argument of the cosine because it takes up too much room. And the second derivative by this thing, it all is going to work out, but only if the dimensions of this part are 1 over c. Boom, boom. And so it must be that omega squared is going to be 1 over the square root of L over c, in the same way that this only worked out if omega squared was equal to k over m. So if you like, there's a proof. We need to memorize it. This could be Wilk. I don't know. Maybe you can do better. We don't have bottoms turned upside down to help us out here. You just need to memorize that. Good stuff. And that's the end of the show.